In this video, we begin a formal consideration of how to test hypotheses regarding two proportions from independent samples. Do note, this has to do with tests of hypotheses regarding two proportions from independent samples. So we consider a motivating example, and here we're told about a survey that asked, how many tattoos do you currently have on your body? Of the 1,229 males surveyed, 192 responded that they had at least one tattoo. However, of the 1,050 females surveyed, 126 responded that they had at least one tattoo. Well, based on the data collected, here are some questions we can ask. Does this evidence suggest that the proportion of males that have at least one tattoo differs significantly from the proportion of females that have at least one tattoo at the alpha equals 0.10 level of significance? Here's another question. Is it possible to construct a 95% confidence interval to judge whether the proportion of males that have at least one tattoo differs significantly from the proportion of females that have at least one tattoo? Can you also interpret that interval? These two types of questions are such kind of questions that we will consider while addressing this topic. But we do need a couple of important basics. So we're going to outline those two basics that we're going to need in order to be equipped in order to answer the questions posed based on the scenario observed. Here are the two things we must learn. One, we must learn how to conduct an analysis that relates to the test of hypotheses regarding two populations based on two independent samples drawn from such populations. Two, in order to answer the second question, we must be able to construct a 1 minus alpha 100% confidence interval for the differences in population proportions based on independent samples. In today's world, there is good news. The use of technology makes this analysis a lot easier. We do need to, however, focus on how we set up the inputs in, or how we serve up the inputs into a StatCrunch, which will be our companion technology, in order to help us conduct each of these types of analysis. But before we go any further, you should note that, as is true for most testing statistics, there are always underlying assumptions that must be validated for the results of any of these two types of analysis to hold true. So we're going to look at the assumptions, or what we otherwise call the model requirements. That has been provided on the next page, which is page 5. So let's start with, how do we look at the assumptions for testing hypotheses regarding two populations? If we have two population proportions, P1 and P2, if we want to test hypothesis regarding these two populations, we must first verify that 1, the samples are independently obtained using simple random sampling or through a completely randomized experiment with 2 levels of treatment. 2, N1, that is the sample size chosen from the first population, the proportion or the sample proportion from the first population, and N2 is the sample size from the second population, whereas P2, as you might expect, will be the sample proportion estimate from the second population. We must also check that each of these are also verified. That is, N1 times P1 at times 1 minus P1 at is at least 10. And the same is true for N2 times P2 at times 1 minus P2 is also at least 10. Then 3, each of the samples sizes drawn from each of the two different populations must be less than or equal to 5% of the finite or of the total population sizes. So to get us started, you should note that I have provided the steps for testing hypotheses regarding two populations. Step 1 is to determine the null and alternative hypothesis, where P1 and P2 are the population proportion for population 1 and the population proportion for population 2, respectively. Then 2, we'll select the level of significance, alpha, whose size will depend on the seriousness of making a type 1 error. If you need to recall what this means, please revert back to chapter 10, where we learned hypothesis testing on a single population. Then 3, compute the test statistic. In this case, you can use the classical approach or you can use the p-value approach. In both instances, we are going to be able to use StatCrunch technology in order to help us do this computation. Then, step 4, we will compare the critical values to the test statistic if we are using the classical approach, or we will compare the p-value to alpha, the level of significance of the test, if we're using the p-value approach. And then finally, we will be able to state our conclusion based on the results of steps 3 and 4. So we begin the first example. In this example, we are told that in randomized double-blind clinical trials of a new vaccine, infants were randomly divided into two groups. Subjects in group 1 received the new vaccine, while subjects in group 2 received a control vaccine. So we have new vaccine and control vaccine. These are the two populations. Now, after the second dose, 122 of the 657 subjects in the experimental group, that is group 1. So let's call this group 1, and then this is group 2. So it means in total, in group 1, we have N1 equals 657 subjects there. And X1 would be 122 out of 657. Whereas in the second case, or the second population, so we're told that after the second dose, for those in the control group, that is the second group, 759 out of 538 of the subjects experienced fever as a side effect. So you have X1 is 79 out of N1, which is 538. Excuse me, this should be X2 and N2, rather. My apologies for that. Now, the question is, does the evidence suggest that a higher proportion of subjects in group 1 experience fever as a side effect than subjects in group 2 at alpha equals 0.10 level of significance? In order to answer this question, the first step is always to verify the model requirements. Those were stated earlier when we said that we always needed to verify the model assumptions or requirements. All right, so let's go ahead and work on that. First of all, we're going to need P1 at, which is always X1 divided by N1, or 122 out of 657. And we're going to need that to check if what the value of N1 times P1 at is. So this will be, what is our N1? That is 657 multiplied by 122 out of 657. This will give exactly 122 because that crosses out. And so this is definitely greater than or equal to 10. So it passes the first model, the second model requirements. Okay? The second part of this is to check, again, if you recall, that we also need to check the second part too. You will observe that for the first case, the answer narrowed down to 122. So in the second case, again, our N2, P2 at, will be N2 is 538 multiplied by P2. P2 is X2 all over N2. So that will be 79 out of 538. And this gives us 79, which is also at least greater than 10. So, as far as we're concerned, requirement 2 is satisfied. That is, to take you back memory lane, let's erase this quickly. Requirement 2 is met. Then, we are also told that the samples are independently what? Must be independently obtained. If you observe closely in this scenario, these are definitely a case of independent what? Sampling. Because those subjects who were selected to be in group 1 have no connection with those who were not exactly dictating those who were going to be in group 2. So this is an instance of independent sampling. And step number 3, or requirement number 3, is also met, that each of the sample sizes are at least 5% of the population size for each sample. So with that said, we move on to step B, where to determine the null and the alternative hypothesis. Our null is written as H0, alternative as H1. Well, the null hypothesis, or the interest here, is to see if, what we want to test is to see if a higher proportion of subjects in group 1, that is, proportion in group 1, is it going to be higher than those in group 2? That is, we want to check if proportion 1, is it going to be higher or greater than proportion in group 2? That is what this question wants us to test. So the null hypothesis will be the null hypothesis of equality, or the hypothesis of equality. Now, we're going to need to find the test statistic for this hypothesis test. How do we do that in StatCrunch? Let us see. Before we begin, note that in this case, you'll be able to complete question C and question D at the same time in StatCrunch. Let me show you how to do that. What will you need in order to be able to do this correctly? A couple of things. Let me erase this a little bit. And you're going to need the x1 out of n1 and x2 out of n2. You're also going to need your alpha in this case. So let's see how that is done in StatCrunch. So in StatCrunch, I am going to go to statistics or stat, and I will go to proportion stats. This time, to sample. Then go to with summary, because this data set has been summarized. We do not have data in columns. Click on with summary. Then in sample 1, you want to note that that will be 122 out of 657. So let's type that in, 122 out of 657. Then for sample 2, what do we have? We have 79 out of 538. So 79 out of 538. And then the next thing to note is we would like to perform hypothesis test for P1 minus P2. And in this case, you want to ensure, as a matter of expediency, that you set the right direction of the alternative hypothesis that should be greater. So I'm going to go ahead and do that. Choose the drop-down arrow, or click on the drop-down arrow and choose greater than. And then also make sure that to get your p-value and your critical value, or to get your test statistic too, you want to make sure you show critical value and indicate your level of significance. In this case, our alpha is 0.10. So I'm going to adjust that to 0.10. Here you have that. And compute. And voila. So what you need here is the Z statistic. This is your test statistic, and this is your P value. So I'm going to carry these values over to our workbench. So here on my screen, I can see the test statistic we obtained and the P value that we got from StatCrunch. Before we go any further, here is a simple, very friendly advice. Try to sketch the critical region. That is, draw the normal distribution, and from the alternative hypothesis, I can tell that the critical region is only on one side of the tail. That is, this is on one side, on the right tail, and I'm going to write this. What value cuts it off? That is the critical value. So going back, my critical Z value is 1.28. So I'll take that back. This is 1.28. So values to the right, here is the rejection region. If this is the rejection region, then I need to check, where does my 1.79 fall? 1.79 on the number line is bigger than 1.28. So it is definitely further to the right. It falls in the rejection region. Remember, when your test statistic falls in the rejection region, what do you do to the null hypothesis? So this means I should, since 1.79 is greater than 1.29, it falls in the rejection region, RR. So that means I should reject the null hypothesis. If I'm rejecting the null hypothesis, it means this is the bad one and this is the good one. What we want to test, which is the alternative hypothesis, has sufficient evidence for it. So we can say that there is sufficient evidence in favor of the fact that there is a higher proportion of subjects in group 1 who experience fever as a side effect than subjects in group 2. So there's sufficient evidence in favor of the alternative hypothesis. And what does that mean to everyday person? It means that if we are to draw a conclusion for this test, I'm going to make a quick jump here, and then we'll be back to part E. The conclusion for this test is as follows. We are rejecting the null hypothesis, which means that we have sufficient evidence in favor of the alternative hypothesis that we wanted to test. And that means we can conclude that a higher proportion of subjects in group 1, represented by P1, experience drowsiness as a side effect than subjects in group 2, represented by P2, at the alpha equals 0.10 level of significance. Now, observe earlier that we said earlier that the p-value is 0.037. What does this mean? What does this p-value mean? Let us interpret that in question E. Note that 0.037 is equivalent to 37 divided by 1,000. So this means that if the population proportions were equal, that is, if the null hypotheses were true, one would expect a sample difference proportion greater than the one we observed in about 37 out of 1,000 repetitions of this experiment. With that, we come to the end of that question. We shall consider more examples in the next video. So please do watch the next video.